Hello and welcome to our first lesson. So we're going to start with some algebraic techniques content today. We're going to be focusing on factorization. So by the end of the lesson, you will have learned to identify algebraic expressions, how to identify the greatest common factor of algebraic expressions. You will have looked at factorizing by pulling out a greatest common factor. You will have looked at factorizing monic quadratic expressions, non-monic quadratic expressions, perfect squares, difference of two squares, and you will have looked at factorizing by completing the square. And all of these we're then going to apply to solving some equations, and also we're going to apply this factorization to simplifying some scary looking algebraic fractions. We got a lot to do. First, I want to go over some vocabulary. What is a numeral? A numeral, we're going to call it a normal number. It can be multiple digits, right? So 2 is a numeral, 12 is a numeral, 212 is a numeral. What is a variable slash pronumeral slash parameter? There's a lot of names for this thing, but essentially it's a letter that we use to represent an unknown numeral, right? So it could be X, could be A, could be Z. Sometimes we even use Greek letters like theta. What is a term? A term is a grouping of numerals and pronumerals that are not separated by plus or minus signs. So that could be like 3x squared, right? If we have 4 plus 5x, this is not a term because there's a separation here by a plus or a minus sign. So in fact, this is a term on its own, and this is a term on its own. What are like terms? Like terms are different terms that have the same pronumerals with the same powers. The order is unimportant. So none of these are like terms. But if I had another set of terms here, say I had negative 2x squared minus 6x plus 10, now I have three pairs of like terms because this is like terms with that, because we have the x squared. And this is like terms with that because they both have an x in them. And then this is like terms with that because they don't have any pronumerals in them. I want to point out as well that if we had like 5xy and negative 3yx, these are also like terms because they have the same pronumerals, even though the order is different, right? If that was x squared, this would have to be x squared here. They would not be like terms if we had x squared y and y squared x, because even though they have the same pronumerals, they don't have the same powers on those pronumerals, okay? You got to have the same pronumerals with the same powers, and you don't have to worry about the order. What is the coefficient? It's the numeral component of a term. So here, 3 is the coefficient of x squared. Here, negative 2 is the coefficient of x squared. Here, 5 is the coefficient of x. Here, negative 6 is the coefficient of x. Notice that I'm including the sign in front of the term with the coefficient. What is a constant? Well, a constant would be like this 10 or this 4. It's a term that has no x involved. And what is a factor? A term which another term can be divided by. There's a lot of definitions for factor, but with the algebra that we're looking at, we're going to start looking at factors in a very abstract sense, and saying things like you can divide by without a remainder is going to become a little bit less useful of a definition. But we could say, for example, if we have negative 2x squared, we could say there's a factor of negative 2, a factor of x, and another factor of x. We could also say that it has a factor of 2x, or we could say that it has a factor of x squared, right? In this case, it's 2x times x. In this case, it's x squared times 2, right? There's a lot of ways we can break something into its factors. In fact, in both of these, I should also point out that we need to multiply by negative 1, or we have not gotten back to negative 2x squared. Cool. Now that we've gone over these basic definitions, I think we're ready to get into the fun stuff, and we're going to start with talking about what is an expression. An algebraic expression is one or more terms all connected with plus or minus signs. 3x squared, this is a positive term. We have another term, which is 5x, also a positive term. And then we have another term, which is negative 2. Okay, so When we're breaking up an expression into terms, we always have to pay attention to what the sign in front is, or if it's the first term, like with the 3x squared, and there's no sign in front of it, that means it's positive. When you're working with algebraic expressions is putting them in order. So if they're about x's like this, we want to put the term with the biggest power of x first and then go in descending order. So if you got a question with an expression like this, the first thing you would do is you would rewrite it. You would say, okay, this is going to be negative 6x cubed minus x squared plus 7x minus 4. Right? So we have the power of 3, then the power of 2, this is the power of 1, and this one, there's nothing there, we could say it's a power of 0. We have 3 negative terms and 1 positive term. Now, this next one is an interesting example, and the reason it's interesting is this is all one term. This is all one term. But that term, this expression, is one term made up of the product of two smaller expressions. And these two smaller expressions each have two terms within them. But this whole thing is one term because nothing here, we can't like add or subtract to break this up. Here, like if we added 4, that 4 would go away. Here, if you add 3, you just have a plus 3 on the end. It doesn't go away. So this is one term. Now, this one term can be expanded. So this is what we call a factorized form of an expression. And if we expand this out, we're actually going to get this. And you can see here that we have 3 terms. So we've got this one is positive, and then this guy here is negative. So these two are actually equivalent. They're the same thing mathematically, but these are two different expressions. One of them is one term, one of them is 3 terms. When we factorize expressions, one of the things we're aiming to do is to turn something with multiple terms into something with one term. And that allows us to do some interesting things. We're going to look at one of those things today. It'll come up called the null value theorem. So just hold that in your mind. We're going to look at it. We also need to understand a few basic expression types. This is a family of expressions called polynomials. And the pattern here is you'll notice that this has no x, this has 1x, this has 1x squared, this has 1x cubed, this has 1x to the 4, this has 1x to the 5. So polynomials are expressions with different powers of x, and we classify them based on what is the biggest power of x. This here we call a constant polynomial because there's no x. So if x changes, the value of 8 doesn't because there's no x. So changing x doesn't change it. In this case, though, as x changes, the value of this expression changes. And it changes by however much x changed multiplied by the coefficient, multiplied by 2. And that is what we call a linear change. So this is a linear polynomial. The next level of polynomial is called a quadratic. The next one is called a cubic. The next one is called a quartic. The next one is called a quintic. You're not going to really see many other than these and a little bit of cubics. We're not really going to touch these at all. And something that I want you to know is we can use other names to describe the polynomials. This is a polynomial of order 0. This is a polynomial of order 1. And what I'm naming is the power on the x. So this is a polynomial of order 2. This is a polynomial of order 3. And you'll notice that I just care what is the highest power of x. It actually doesn't matter whether or not the other powers of x are present, right? Here we have 3, but we also have 2, 1, and 0. Here we have 4, but we just have 3. We don't have 2, 1, and 0. Here we have 5. We don't have any of the others. That's fine. We call it a polynomial of order 5 because that's the largest power of x. We're going to spend a lot of time today looking particularly at quadratic and linear expressions. There will be some cubics. You're not really going to do much beyond that in high school. We will see some things when you get to calculus about how these different polynomials connect and how we can transform them from one order into another order, and that has some physical implications. So we'll get to see that, which will be fun. Now we need to look at factorization. But before we can factorize things, I want to make sure that you remember how to go in the other direction, how to expand brackets. So the first thing that I want to explain is how to do it using FOIL. So you should know this acronym, which is firsts, outsides, insides, and lasts. Okay? So in this case, the firsts are the 2x and the x. So we multiply them. So that's going to give us 2x squared. Then the outsides are the 2x and the 4. So that's going to give us 8x. Then the insides are the negative 3 and the x, negative 3x. And then the loss are the negative 3 and the 4, negative 12. Now we collect our like terms, so we have 2x squared plus 5x minus 12. So this is our expanded expression, and if we factorize this, we will end up back where we started. Now, the important thing about FOIL is just the pattern that the first term in the first bracket got multiplied by both terms in the second bracket, And then the second term in the first bracket got multiplied by both terms in the second bracket. Okay, that pattern will apply in these ones as well, even though we can't use FOIL exactly because we have three terms here, right? So it's not just about the first and the last, there's like a middle one as well. But we're going to follow this pattern. We're going to take the x, we're going to multiply it by the x, then by the y, then by the 3, and then we're going to take the 2, and we're going to multiply it by the x and the y and the 3. So x times x is x squared, x times y is xy, x times 3 is 3x, 2 times x is 2x, 2 times y is 2y, and 2 times 3 is 6. Now we collect our like terms. We have x squared plus xy plus 5x plus 2y plus 6. So we weren't able to collect many. We could just group the 3x and the 2x into a 5x. All right, now here we're going to do exactly the same thing, except now we have three terms in the first bracket as well. So we'll do x times each of these, then 2 times each of these, then a times each of these. X squared plus xy plus 3x. So that's all of the ones from here. Now I'm going to take the 2. So plus 2x plus 2y plus 6. So that was all of the products that come from the 2. Now I'm going to do the a plus ax plus ay plus 3a. Now if we collect our like terms, again, we don't have many that we can collect together. It's just going to be the 3x and the 2x, I believe. So we'll have x squared plus xy plus 5x plus 2y plus 6 plus ax plus ay plus 3a. And you can see that this is a lot of messy stuff, and it's actually a lot easier to look at when it's in the factorized form in those brackets. Generally speaking, you will not need to factorize expressions where you're going to end up with 3 or more terms in your brackets. We're only going to look at factorizing expressions where you're going to end up with 2 terms in the brackets, generally speaking. There will be 1 or 2 exceptions. Here we have this one to expand. We need to remember that that squared simply means that we're doing a plus b multiplied by itself. So applying FOIL, a times a, that's the first. Outsides is this a times this b, so plus ab. Insides is this b times this a. I'm going to write it as ab again so I can see that we have like terms there. And then last is b times b, so plus b squared. And if we collect our like terms, we have a squared plus 2 amounts of ab plus b squared. It's really important to recognize that there's this middle term, right? If we have a plus b all squared, it's not just a squared plus b squared. There's more to it. And there are some really good explanations of why that is, but you should kind of, everything we're doing today should be revision, so I'm not going to go into much detail. I'm just going to expect you to kind of understand. All right, and now this one is called the difference of two squares, and you're going to understand once we get there. So first we have a times a is a squared, and we have a times negative b, so that's going to be minus ab, and then we have b times a, so plus ab, and then we have b times negative b, so minus b squared. And when we collect our like terms, these two cancel out, and so we're left with a squared minus b squared, or in other words, the difference of two squares. Let's move from expanding. We're ready now to look at factorizing. So factorizing comes in a few flavors. I'm going to do a lot of examples. What I would recommend that you do is pause the video, see if you can do these without seeing my solution, and then play the video again. This one up the top, I'm going to try and extract a common factor from all of these terms. So I can see that we have a factor of 6 in everything and also a factor of x in everything. So I'm going to say this is 6x. Now to get 36x cubed, we need to multiply that by 6x squared. To get the negative 24x squared, we're going to have to multiply by minus 4x. And then to get the 6x at the end, we just have a plus 1. What's in the brackets cannot easily be factorized further. It is technically possible always to factorize a quadratic polynomial, but in this case it is not easy and we do not have to do it. When we're factorizing expressions, we may find that they have x squared or they have x squared multiplied by something. If it's just x squared, we call it a monic quadratic. If there is something multiplied by the x squared, we call it a non-monic quadratic. What we need to do here in the first example is recognize that we can factorize away the 3 and we can turn it into a monic quadratic. 3 times x squared minus 4x minus 21. This is now a monic quadratic in the brackets. So let's look at how we solve this question here. What we're going to do is we're going to look for two numbers, and they have to add to the coefficient of the linear term. They have to add to negative 4, and they have to multiply to the constant term. So two numbers, when we add them, we get negative 4, and when we multiply them, we get negative 21. So because the product, the negative 21, is less than 0, that tells me that we're going to have a positive number and we're going to have a negative number. And because this is a negative 4, this tells me that the bigger value is going to be the negative number, and that value is going to be bigger than the positive number by 4. What we're working with here is going to be a positive 3 and a negative 7, because 3 minus 7 is negative 4. 3 times negative 7 is negative 21. Okay, so that's 3 times. Now I'm going to break this negative 4x into the 3x and negative 7x that we just figured out it's made of. So we have x squared plus 3x minus 7x minus 21. Okay, so you can see these expressions are equivalent because if we just combine the like terms of 3x and negative 7x, we get back to the negative 4x. But now we can factorize. So we say 3, and then here we have a common factor of x, and here we have a common factor of negative 7, and now we have this common factor of x plus 3. So it becomes 3, x plus 3, x minus 7. The key insight here is that the values we thought of before, the 3 and the negative 7, right? Here we had the positive 3 and the negative 7. They come up in the answer. When we're solving a monic quadratic, the two numbers we think of, they're going to be the two numbers we need. We could have jumped straight to 3x plus 3, x minus 7 without doing all that extra work. And so that's what we're going to do for the next and every other monic quadratic. For the non-monics, we don't have such a nice shortcut, and it's going to be a little bit more work. So here we have a monic. What are two numbers that add to 10 and multiply to 16? Everything's positive. That makes it easy. This is going to be x plus 2, x plus 8. Awesome. Okay, so now we have non-monics. So we're going to do something slightly different. We still want to find two numbers that add to something and multiply to something. The thing that they're going to need to add to is still going to be this term here, the coefficient of the linear term. But what they're going to multiply to is going to be the product of the constant term and the coefficient of the squared term. Okay, so we need two things that add to 5 and that multiply to negative 24. Negative 24 is the product, which means one of them's got to be negative and one of them's got to be positive. So two numbers where they have a difference of 5, the bigger one is positive, and they multiply to 24. So I'm going to say positive 8, negative 3. Now we don't have a shortcut in this one. We have to do the long work. We're going to have 12x squared plus 8x minus 3x minus 2. So this is going to be 4x, and we're going to have 3x plus 2, and then I'm going to say minus 3x plus 2. There is an invisible number here I didn't write. That's like a minus 1 there. And then we can factorize that as 3x plus 2 times 4x and negative 1. And that is our factorization. We have to do the middle step. There's no way from getting the 8 and the 3 in the first step that we can know what the last step's going to look like. There is another method for factorizing non-monics, which I'm going to show you. It's called the cross method. To do the cross method, we're going to look at this second one here. We start by doing a cross. Now on this side here, we're going to put the factors of the coefficient of x squared. And on this side here, we're going to put two factors of the constant term. Okay. Now, the factors that go here could be 1 and 4 or 2 and 2. Either of those would work. We don't know yet which one it's going to be. We're going to have to experiment. The factors that go here could be 12 and negative 1, could be negative 12 and 1, could be 2 and negative 6, could be negative 2 and 6, could be 3 and negative 4, could be negative 3 and 4. We don't know. So there's a bit of guess and check that goes on in the cross method. The more you do it, the easier it's going to be. I would recommend this method for most students, but I want to show you this one because it can be quick if you master it. So I'm going to start by doing 2 and 2, and then this number and this number I will multiply, and then I will add those to the product of this number and this number. And when I do both of those multiplications and add them together, I want to get that middle term, that negative 2. So let's see, if I 2 times 3 and 2 times 4, 6 and 8 is going to give us a difference of 2. So that's good. And we need the bigger one to be negative. So I'm going to say negative 4 and 3, right? So 2 times 3 is 6, 2 times negative 4 is negative 8, 6 plus negative 8 is negative 2. Now, the way we turn this into our answer is pretty straightforward. We're going to put an x here and an x here. This is a negative, this is a positive. So our answer is going to look like this. 2x minus 4, 2x plus 3. Now for each of these, you can expand them out and you should get back to exactly what we started with. You can choose which of these methods you like. I find this one is more confusing for students who are new to it, but it's faster for students who take a lot of time to do a lot of practice. For most students, this is easier to understand, easier to remember, and easier to get correct. Moving on, there are two patterns we need to be able to recognize and factorize. Firstly, we have perfect squares. So this number will be double something, and this number will be that thing squared. So in this case, it's 1. This is going to factorize to be x plus 1 whole squared. In this case, this is double 5, and this is 5 squared. So this is x plus 5 whole squared. This one's a little bit different. In the last two, they were monics. Now we have a non-monic. There are a couple of ways to approach this. Firstly, I'm going to show you the full answer. We're going to say this is 3x plus 6 whole squared. However, we could pull out that factor of 9 first to turn it into a monic. Now this is double 2, and this is 2 squared. So we have 9 times x plus 2 squared. This is 3 squared times x plus 2 squared. Or we could say 3 times x plus 2 whole squared. Or we could multiply that 3 into the brackets, 3x plus 6 whole squared. In fact, if you wrote this as your final answer, this would not count as being fully factorized. The fully factorized version is this top one, 9 times x plus 2 all squared. So those are examples of perfect squares. They're perfect squares because it is something squared instead of having two different brackets. Now these are called the difference of two squares, and when we factorize them, we basically take the square root of each of these numbers, and we're going to have one set of brackets where we add them, and the other set of brackets where we subtract them. The one that has the negative in this expression is the one that will have the negative when we do the subtraction. So this will become x plus 6 times x minus 6. This will become, now we normally wouldn't treat this as a difference of two squares, but I'm going to show you that we can. This becomes x plus the square root of 2 times x minus the square root of 2. This will become 3x plus 1 times 3x minus 1. And this one, we have to pull out the factor of 7 first. I'm going to make it a negative 7. So this becomes 1 minus 4x squared. And so that will be negative 7 times 1 plus 2x times 1 minus 2x. Awesome. Okay, there's one more type of factorization you have to know, which is called completing the square. So firstly, I just want to show you, this is a perfect square, which means we do this bracket times this bracket. And when it gets expanded out, we have this pattern. We have a squared, that's the first. And we have two amounts of ab, because the outsides are ab and the insides are ab. So we have two of them. And then finally we have loss, which is this term squared. Okay, so to complete the square, we're going to use this pattern. Suppose we have an x squared plus sx. And we want to say that it fits this pattern, that it is a perfect square. Well, that means, here's our x squared, right? A is x. So we have 2b, two amounts of something multiplied by the x. And the thing we have two amounts of is whatever goes here. Okay, so what that means is that this s, that must be equal to two amounts of b. In other words, if s is two amounts of b, that means that b is half of s. Okay, so to complete the square, we're going to say this is x squared plus sx. Then we're going to add something and subtract something. We're going to say s over 2 squared, and then we're going to minus s over 2 squared. This is a filthy, disgusting, sneaky mathematician's trick. We added something and we subtracted it away. So this line is exactly equal to the line above it, but it looks different. The reason is now we have this part where the middle term is double something. It's double s over 2, and the last term is that thing squared, right? So just like here, the middle term is 2b times a. Here it's two amounts of s over 2 times x. And then here we have b squared. Here we have s over 2 squared. So when we factorize this, it's going to look like x plus s over 2 squared, and then we just have this guy left over, so minus s over 2 squared. Okay, so here we have factorized this as a perfect square. We completed the square, but we have this extra term left over. This is a common thing that happens. I'm going to go through a few examples here, and then we're going to take it further in a minute. Half of this is 3, so this becomes x plus 3 squared, and then we have minus 3 squared. In this case, I'm going to pull out that common factor of 3 first. So we have 3 times x squared plus 4x. So half of that 4x is 2. So that means we have 3 times x plus 2 squared minus 4. Or we could expand out those brackets and we would have 3 times x plus 2 squared minus 12. I'm not going to do that right now. This is enough. And in this last step, we also need to get rid of that factor of 7. So here's what I'm going to do. I'm going to say that's equal to 7x squared plus 8x plus, now 20 is hard to divide by 7, but it's easy to turn into a fraction. So half of that 8 is going to be 4, so it's 7. And then in here we have x plus 4 squared. Then we're going to have minus 16 plus 20 over 7. And we can collect our like terms here. I'm not going to do that right now, because the important thing is that you can see that we've collected this up into a perfect square, and we've got this term to correct for it. We're going to do some more examples in a minute, and in those examples, I absolutely will have to collect the like terms. And that's because we're going to be using this technique to solve equations which are not easily factorized. I want to go back over one thing there, which is this one. We got it to be 3, and then in brackets, we had x plus 2 squared minus 4. I said this was enough, but there is something else we can do. And the reason is, here we have a squared term, and then this is also a square number, and we're taking the difference. So this is a difference of 2 squares. So we can factorize it further like this. We'll have 3, and then we're going to have x plus 2 plus 2, and then we're going to have x plus 2 minus 2, right? Because x plus 2 is the square root of x plus 2 squared, and then the plus 2 and the minus 2, we get them by square rooting the 4. And so, collecting our like terms here, we have 3 times x plus 4 times x. Or I would prefer personally to write it as 3x times x plus 4. If we were really smart, we would probably have realized that we could have done this all along. We have 3x squared plus 12x. There's a common factor here of 3x. What do we need to multiply by in the first bracket? By x. And what do we need to multiply, sorry, in the first term? And what do we need to multiply by in the second term? It's a 4. And so we could actually have gotten this answer with way fewer steps if we were not specifically practicing completing the square. Here are the first set of examples. Now I encourage you to pause the video here, write these out, and attempt these. And then, once you've had an attempt at them, you can press play, and I'm going to go through every single one of them and show you how I solve it. And that way, hopefully, you'll be able to check your answer and demonstrate that you know what you're doing. And if there are any that you're stuck on, you'll be able to see the worked solution. Okay, so I'm going to go through these questions using type math. I can see that there's a factor of 4x throughout the whole expression. So if I pull it out, that becomes a 2x squared. This is going to become a negative 3x, and this is going to become a plus 1. Now, what's in the brackets there can be factorized, I think. So we're going to look for two numbers. They've got to add to negative 3, and they've got to multiply to the product of 2 and 1. So in other words, they multiply to negative 3, and they add to 2. And I'm going to say negative 3, sorry. In other words, they add to negative 3, and they multiply to 2. So I'm going to say negative 2 and negative 1. So we can say this is negative 2x minus x, and then we can do some factorization. So this is going to be 2x times x minus 1. And then here, I'm going to pull out the minus sign. And remember, there's a minus 1 here. There's a 1 that we haven't written, but it's there. Okay, so in this case, we have that 1. So we've got 2x minus 1 times x minus 1. So this is our full factorization here with the 4x still at the front, and we can get rid of that set of brackets. This is what our final answer should look like. Okay, so next one. In this case, we have 5x as our common factor, and so here it's going to be multiplied by 3y, and here it's going to be multiplied by 2x, and that is our final answer. Okay, so for this one, we have a monic quadratic, and we need two numbers that add to 7 and multiply to 12. That's going to be 3 and 4, and so we can just say that our answer is x plus 3, x plus 4. That is a completely acceptable leap to make in your working out. Okay, this one here is a difference of 2 squares, so it is going to be 2x plus 3 times 2x minus 3, just like that. Okay, this guy here. Now we've got a algebraic fraction. And when you have a question like this, typically you're going to do some factorization and then things are going to cancel. So to factorize the numerator, we need two numbers that add to 5 and multiply to 6. It's going to be 2 and 3. So we've got x plus 2, x plus 3. And we probably could have guessed that we were going to get that common factor, that factor of x plus 2, which allows us to cancel the denominator entirely. And so our answer is x plus 3. Okay, moving on. This is a difference of 2 squares. We have x plus 6y, x minus 6y. Easy. In this case, we can pull out a common factor before we get started. So that common factor is going to be a 3y. So this is going to need to be multiplied by 2y squared. Here it's going to need to be multiplied by y, and here by negative 1. Now, can we factorize what's in the brackets? We would need two numbers that add to positive 1 and multiply to negative 2, which I think would be positive 2 and negative 1. Now, we can't jump straight to the answer. The reason is it's not a monic quadratic, so we have to go through the factorization steps. So here we can say that's 2y times y plus 1, and then here we're going to say that's this guy. And so that means we can recognize there's a 1 there, and this will be our final answer, and we can get rid of that set of brackets as well. So this is our final answer for that question. This one here, let's have a look. We have a common factor here of 5x, so I'm going to pull that one out. And so that factor goes, and that one goes. This will become 25. Now we have a difference of 2 squares, so this becomes a plus 5 times a minus 5, and that will be the end for that question. Okay, so for this one now, It's actually a very easy one because we have a common factor of x plus 3 for each of these terms. So that means that x plus 3 is going to be multiplied by x squared, and it's going to be multiplied by -4. And that will be, ooh, but this is not our final answer. I hope you spotted that now we have a difference of 2 squares, which means that this first bracket becomes x plus 2 times x minus 2. And that is our final answer for this question. Okay, so I've thrown in at the end here a bunch of examples with algebraic fractions. So let's jump into these ones. For this one here, we have a difference of 2 squares in our numerator. So this will be a plus b times a minus b. And the denominator here, we have a times a plus b, which means that we can cancel out the a plus b's. And so our answer is just going to be a minus b over a. That's our final answer. Okay, this guy. If we factorize our numerator, two things that multiply to 6 and add to -5 will be -2 and -3. So we have x minus 2, x minus 3. And then we need two things that add to 1 and multiply to -12. That's going to be +4 and -3. We've got x plus 4, x minus 3. Now, we can do some canceling. We can cancel the x minus 3 on the top and on the bottom. And then we no longer need to write it with brackets. And so this is our answer here. And I should have put in equal signs. Cool. So that's our final answer for that question. 2 to go. Now, in this one, we have the product of two fractions. I have here an example which is a multiplication and an example which is a division. I have not put in examples of addition and subtraction. They can also be tricky in their own way. In fact, they can be trickier in their own way. That's something that you should look at. Your textbook will have a bunch of practice problems of that. Okay, so here, what adds to -2 and multiplies to -3, that'll be -3 and +1. What adds to -4 and multiplies to -5, that will be -5 and 1. Then this is x plus 5, x minus 5. And this one's already factorized for us. So the x plus 5s, they're going to cancel. And this x minus 3 is going to cancel with the one up here. And this x plus 1 is going to cancel with this one. And then this x minus 5 is going to cancel with this one. And so our answer is just going to be 1. That's it. Easy. Okay, last one. Let's see. So first thing I'm going to do is I'm going to factorize. Obviously, to turn this into a multiplication, we're going to have to flip this second fraction, but I can see right away that this can be simplified a lot, right? We've got the x squared on the bottom, that can cancel with the x squared on the top. We've got the y on the top, we'll cancel with one of the y's on the bottom. 5 on the bottom, we'll cancel with the 5 on the top, leaving a 2. Now, if we factorize this, we can pull out a common factor of 4x. That's 4x times 3x minus 1. And then down here, we have x times 3x minus 1. Cool. So we can change this down to say times y over 2. And we can cancel out that bracket with that bracket and that x with that x. And this is, oh, we can also cancel out a 2 here with the 2 here. And so our answer is going to finish as 2y. All right, so that was a big set of practice problems. If you didn't understand any, you have your work solutions here. And you're welcome to ask me any questions that you have about how I did them. If I made a mistake, maybe I did. Maybe you can catch it and correct me. But we are not finished because now I want to talk about what I foreshadowed, the null factor theorem. The null factor theorem says if we're multiplying two things, so here I have written two things, we've got an x and we've got a y, and they're multiplying to give us 0. This is possible only if x is 0 or y is 0. Maybe both are 0, but it's not possible that neither of them are 0. So this is going to be the key we need in order to take what we've learned about factorization and apply it to solving some equations. So let me work through these ones here. So if we take this first one as an example, what adds to 13 and multiplies to -48? It's going to be 3 and -16. Sorry, I got signs wrong. It's going to be -3 and 16. So we're going to have x minus 3, and then we're going to have x plus 16. Now that's equal to 0. That means that either x minus 3 equals 0 or x plus 16 equals 0. If x minus 3 equals 0, that tells us that x equals 3. And if x plus 16 equals 0, that tells us that x is equal to -16. And so what we say is that x can be equal to -16 or 3. There are two correct answers here. Why do we have two answers? That's a good question, and it's beyond the scope of what we're looking at today because we're just looking at the algebraic techniques, but there are graphical reasons you can understand with a picture why we get two answers to this question. Okay, going on to the next one. Here we have a non-monic. So first thing I'm going to do is I'm just going to divide everything on both sides by 3. So on the right-hand side, 0 divided by 3 just disappears. On the left-hand side, I can do this. And so this means I want two numbers that, and I can pull out a factor of x. I can't divide away the x like I did with the 3. And the reason I can't is I don't know if x is 0 or not. And if x is 0, then if I divide away the x, I will lose. Firstly, dividing by 0, I'll destroy the universe. And secondly, I will lose the ability to find the answer that x is equal to 0. It will be gone. So I have to, even though with the 3, I could just make that factor disappear, with the x, I have to keep it here. Let me just get some space. Okay, so two things that add to -1, and they're going to multiply to -6, because it's a non-monic, so we have to do 2 times -3. Add to -1, multiply to -6, so -3 and 2. And so if I factorize this now, I can pull out an x here, and just chuck some brackets there. I have to remember there's a 1 in front, so this is going to become this guy. I can get rid of these big brackets. So now when I apply the null value theorem, I actually have 3 things that are being multiplied. This guy, and this guy. So let's work through these one by one. If we take the first term, it means x equals 0. Cool. That's awesome. That was easy. Okay. If we go for the next one, we've got x plus 1 equals 0. We have to do one extra step that says that x equals -1. And if we take the third set of brackets, we've got that 2x minus 3 equals 0, which means that 2x equals 3, which means that x is going to be equal to 3 over 2. We can now say, therefore, x is equal to -1, 0, or 3 over 2. We have 3 answers. As a general rule, with polynomials, the number of answers is equal to the power of the highest power of x. This is a cubic because it's got that power of 3 there. So we have 3 answers. Okay, in this case, I'm going to pull out a factor of 7. And now I can see that this is a perfect square. That's x plus 1 whole squared. And so that means that x plus 1 equals 0. There's no other way that this thing could be equal to 0. X plus 1 must equal 0. And so I can say that, which means that x must be equal to -1. Now, you might be asking, why did I just tell you that the number of answers you get will be equal to the highest power, and then immediately show you an example where we have a power of 2, but we only have 1 answer? Well, technically, what we would say is that we have 1 answer, but it came up twice, right? Because this is squared, came up twice. And again, like what I was saying before, there are good explanations for this when we look at a graph, but that's beyond the scope of what we're doing for now. So for now, just be glad and feel lucky that you only had 1 answer. Now, finally, for this one, I'm going to pull out a common factor of 5, which means this will become 4, and this will become 9. Now we have a difference of 2 squares here. So we're going to have 2x plus 3 times 2x minus 3, like that. This means that either 2x plus 3 is equal to 0, in which case 2x equals -3, and x equals -3 on 2, or 2x minus 3 equals 0, in which case 2x is going to be equal to 3, and x is going to be equal to 3 on 2. In other words, x is equal to -3 over 2, or +3 over 2. Now we have worked through all of these examples. Take your time, make sure you understand each of them. Hopefully they're all good. Now we can go a little bit further. We have these 3 examples where these equations will require us to complete the square. It's just not going to be easy to answer them if we don't. I showed you we need to take half of this number. So this is going to become x plus 3 squared, and then we're going to have to subtract off the 9, right? So if I put in the middle step, this is like x squared plus 3x plus 3x plus 9 minus 9. And all of this factorizes to this. And this is left over. So what we're going to do now is we're going to put that 9 on the other side. So we add 9, that gives us a 14. The reason we like this approach is now we can square root both sides. So we have to be careful when we square root that 14. We've got to remember we don't know if it's positive or negative. But what we do know is that it's equal to x plus 3. And so x is going to be equal to -3 plus or minus 14. We're not going to put this in a calculator. We're going to leave it with the surd there. That means we have an exact answer. If we put it in a calculator and we round our decimals, we don't have an exact answer. First thing I'm going to do is I'm going to divide everything by 3. It's going to make life easier. That becomes 3, that becomes 4, and that becomes x squared. Then this is going to become x plus 2 whole squared minus 4. So I'm going to take that minus 4 and add it on here, and then I'm going to square root everything. Make sure I remember plus or minus sign, and then this side square roots, and so then we can say x is equal to -2 plus or minus the square root of 7. Awesome. This one is the hardest one so far. It's going to take a couple little tricks. First thing I'm going to do is I'm going to turn it into a monic. That's going to mean I have to divide every term by 7. Okay, it's a little bit hard with the 20 because it doesn't divide evenly, but that's okay. Now in this step, I'm going to just get rid of that and put it over here, and I'm going to notice that we're going to do this. So these ones here, this becomes x plus 4 whole squared, and then that -16 can get put over here. Now 16, if we were to put it as a fraction over 7, would be 70 plus 42, that's 112. But we're going to minus 20, so that's going to become 92 over 7. So now we can square root that, Doesn't matter what the square root is. It's a hard one to do, but it doesn't matter that it's a hard one to do because we just leave it as a fraction in a square root. And then we can say minus 4 plus or minus 92 over 7. Now there's a pattern. All of mine ended up being a plus in the perfect square. You will not always get a plus in the perfect square. So you will not always have a negative number here. It's just a coincidence that all of mine had a negative number here. But it is always going to be the case that this will be plus or minus something. It may not be in a square root. It might be something that we know how to take the square root of, but it's always going to be plus or minus. To make sure that that's 100% clear, what we've got here are two answers. Okay, we've got the version of this where it's a plus, and we've got the version of this where it's a minus. These are two different answers. Okay, this one is a bit bigger than -4, and this one is a bit lesser than -4. Let's summarize what we've looked at so far. We've gone over a number of vocabulary terms. We've done a crash course through algebraic techniques. Now, you should have learned everything that we've discussed today before. And you should have done your own practice against the examples I showed you. You should have paused the video, had a go, and then checked your answers. Anything that you couldn't do, you should do again. It doesn't matter if you have to look at the solution to get it right, but you should continue practicing the exact same question until you can do it without looking at the solution. Yes, in maths, we want to understand instead of memorizing, but if memorizing is what it takes for you to be able to get these questions right, that's fine, because once you have done it with memorization, the understanding will come more easily later. Now, please do this week's worksheet. Treat it as a practice test. It should take you 1 hour. If you finish early, use every remaining second to check your answers. And if you run out of time, just stop. Don't keep going. You're done. 1 hour is the amount of time I want you to study on that. If you want more practice questions, start by reattempting all the ones that you got wrong. It's also worth trying to make up your own. Some questions work and some questions won't work. And you're going to learn the reasons and the rules that govern that by trying to make up and solve your own questions. You can also ask ChatGPT to make questions. You have to prompt it carefully. You've got to tell it specifically what you want, but it can. But just like when you make up your own questions, sometimes they won't work. When ChatGPT makes up questions, sometimes they won't work. And if you ask ChatGPT for answers, sometimes it will give you answers that are not the correct answer. So you have to be really careful. Next lesson, we're going to be extending the algebraic techniques we've looked at today, and we're going to take it to looking at more surds and also looking at the index laws. So I hope that everything we've discussed was clear. I hope that it made sense. And if it didn't, I hope to see you asking me questions about it soon.